We now know what the scattering matrix is, what the scattering parameters are, and we've shown how we can use them to analyze a circuit, to structure, and find answers. But the question I might ask is, how do we determine these scattering parameters in the first place? How do we measure them, or how do we determine the scattering matrix of some microwave device? And so really there are two questions there. The first is, how do we measure the scattering parameters in a laboratory? If we have a physical device that we've purchased or we've designed and built, how do we go through and figure out what these scattering parameters are? There is a piece of test equipment, a very expensive piece of test equipment called the network analyzer that will go through and take these measurements that will determine the scattering parameters for a multi-port device. Again, they're very expensive, tens of thousands of dollars, a little bit complicated to use. You have to know what you're doing. Oftentimes, well, all the time, it requires a calibration before beginning. You have to define where your port planes are precisely in that calibration and so forth. But you can go through and it will give you a wealth of information about your device. Most importantly, it will give you how it behaves as a function of frequency. So it will go through and test the device at whatever bandwidth or range of frequencies you desire and get the scattering matrix as that function of frequency. So here's another image of a network analyzer, and it appears to be analyzing a bandpass filter here, SMA connectors on either end. So this is a two-port device that it's analyzing. And what this does very physically is it introduces an incident electromagnetic wave propagating down the transmission line to one port, and one port only one incident wave. And then it goes through and measures the scattered waves that result, scattered from the first port and scattered out of the second port here. Does that by measuring the magnitude and the phase, the relative phase at the port planes for these incident and scattered waves, and from that then it calculates the values of the scattering parameters, the scattering matrix. Once it is done with an incident wave on this side, it'll switch and send an incident wave on to port 2 and then measure again the scattered waves at each of the two ports for that case. And by doing those two steps, basically calculating the two columns of the 2x2 scattering matrix for this two-port device, it will come up with then the scattering parameters as a function of frequency. The second question when it comes to determining scattering parameters, though, would be one where we don't have a physical device that we've purchased or we've constructed. Instead, we have a device that we've designed on paper. We have a schematic of that component. We want to know, before we build it, what we think the scattering parameters would be. So we need to do a schematic analysis of a circuit of a network, and from that, ascertain the scattering parameters. And so, as an example, let's say we have this simple two-port device. It's just a lumped series impedance here, and we connect to either port of this simple two-port device a transmission line of characteristic impedance Z0. So both the characteristic impedances are the same at each port. And of course, this is important when we are determining scattering parameters. We have to define not only the device, but also the characteristic impedance of the transmission lines connected to it. So we have everything here where we could determine the scattering parameters. How do we, though, determine the scattering parameters based on this schematic? Oftentimes students struggle with this part. How do I determine the scattering matrix of a device from its schematic? And the thing I want to emphasize here is you know how to do this. Everything that we've learned up to this point has led us to this juncture where we're going to try to figure out how to determine the scattering matrix of a device based on its schematic. Sometimes students, I think, sort of say, well, this is the scattering matrix section, and so I'm just going to forget about everything we've done previously and only apply the things that I've learned here in this section. No, this is going to require an application of everything we've learned through the course to this point. So you need to use a full dollop of all your microwave engineering knowledge to be able to answer the question, what is the scattering matrix of some useful device? The first step in determining the scattering matrix for a device based on schematic is to understand the experiment that is associated with determining the scattering parameters. We go through and determine one column at a time. column 1, column 2, column 3, so forth, depending on the number of ports. And we do that by, for column 1, putting an incident wave on port 1, but only on port 1. We want to ensure that the incident waves at every port other than port 1 are 0. We do that by attaching match loads to them, or we can simply say in our analysis that the wave that is incident on the remainder ports, the plus wave on ports 2 and 3 and 4, for example, are equal to 0. But that is a step that you must understand, that what you're trying to do is set up an experiment. Just like the network analyzer does, it puts an incident wave into one port and then measures the scattered waves coming out all the other ones. You do this then on paper. Set up your schematic with a situation where there is an incident wave on one port, and then try to analyze the circuit to determine the scattered waves coming out all of the other ports. Once you're done with that first port, then you move to the second column, the second port. Put another incident wave onto the second port and do your calculations again, and then to the third and the fourth. However, what we'll find is oftentimes for useful devices, there's a great level of symmetry associated with the device, and so we don't really have to go through and do all the calculations. As we showed in circuit symmetry, even a 4-port device may only have 2 unique values that need to be found, and once we find those 2 unique values, then we can fill in the rest of the scattering matrix. So symmetry is going to be a big help when it comes to doing the analysis. If we have a 4-port device, it seems like we'd have to come up with 16 different scattering parameters, but again, because of symmetry, it turns out often we have far fewer numbers that we need to determine. So this is what then our problem would look at like. We take our 2-port device and we terminate the second transmission line in a matched load, a resistor numerically equal to Z0. And of course that ensures then that the incident wave onto port 2 is equal to 0. The total voltage along this transmission line here consists only of its minus wave voltage, minus wave because it's propagating away from the port. It is the scattered wave. On port 1, however, we're going to go through and allow an incident wave. So we're going to write our telegrapher equations here using both a plus wave voltage and a minus wave voltage. The sum of the two, of course, is the total voltage according to telegrapher equations. This minus wave voltage is the scattered wave from this port. So one incident wave comes into port 1. There is no incident wave on port 2. We have a scattered wave coming out here and a scattered wave coming out here. And what we want to do is evaluate these scattered waves. Determine V1 minus and V2 minus in terms of V1 plus. Now, this is precisely a problem that we did when we talked about solving transmission line problems. Remember, we had a structure, and I said, well, gee, we have these waves, the telegrapher solutions on our transmission line, and we want to go through and figure out, again, what the scattered waves are in terms of the incident waves. We did that, and we did that to understand now how to determine the scattering parameters. So we talked about different ways in that section 9, chapter 9, when we talked about analyzing microwave circuits, and all of those tools that you learned now are going to be valuable to us in trying to determine the scattering parameters. We could solve this problem, and we did. And go back and look, we solved this problem using boundary conditions. This was a circuit that we did 3-4 times, I think, in section 9. We solved it using boundary conditions. We solved it using equivalent circuits, where the input impedance, looking into the structure, we know is Z0, and we combine that Z0 with this impedance, and then we got a new load impedance here, and then from that we're able to determine the scattering parameter, or the scattered wave, V1 minus, and then we unwrapped it with the accordion. We took the answer and we values here, and we propagated it back to this side so we could determine what V2 minus was. So we did the accordion, equivalent circuits down and then back up again. We also went through and we used odd-even mode analysis to analyze this circuit. It has a plane of bilateral symmetry here, and we went through and showed that we could use a virtual short and a virtual open to analyze the structure. And of course, for all three of these methods, we got the same exact answer. Every valid method is valid. And so we can take those results now and then go through and determine the scattering parameters of for this device. Now, we're not going to go back and redo all these things. You can go back and look at your notes. Again, the answers were the same. We're going to start with those answers and then finish this problem of what are the scattering parameters of this device. But again, the heart of this analysis is the stuff you learned in chapter 9. analyzing microwave circuits, the techniques, boundary conditions, equivalent circuits, the accordion, odd even mode analysis, whatever you want to use, whatever is valid, you need to do that analysis. The most important thing is to set up the experiment. Again, terminate things and match loads. Have only one incident wave. Once you get the experiment set up, then analyze it on paper. All right, using these tools. And then when you're done with that analysis, you can construct, finally, the last step, determine the scattering parameters. So these are the results that we obtained from our analysis of that circuit. Again, we did this in Chapter 9. We did it 3 different ways. Got the same answer every time. And we're going to start with this. All right, we're not going to redo that analysis. We have this, and now what do we do? Well, now we take these values and determine explicitly the incident and scattered waves and evaluate them at the port plane so we can determine the scattering parameters. So once again, I emphasize one of the main reasons we did this study of how to analyze microwave circuits is so eventually we could then determine their scattering parameters. So don't forget the tools in your microwave analysis toolbox. Again, I see this over and over again where students struggle with this chapter, section 11 on scattering parameters because they're not using any of the knowledge that used from Chapter 9. Chapter 9 is inherent and is crucial to being able to determine the answer to these problems. So we take the results that we got for that circuit. We notice we found V01 minus in terms of V01 plus, and so we replace V01 minus in the minus wave, the scatter wave on port 1, and insert the value that we determined. Notice now it's in terms of V01 plus. Same thing for the scatter wave at port 2. We determined V02 minus in terms of V01 plus. There is that value, and so we insert it in there. And then, of course, we know the incident wave on port 1, it is dependent on V01 plus as well. So now we have explicitly the 3 waves, one incident on port 1, one scattered from port 1, and a third that is scattered from port 2. From this, we can determine the scattering parameters. All right, so what we have to do to find scattering parameters is to evaluate these wave functions, the scattered and incident waves, at the port planes. And I emphasize this and put it in red and big capital letters because oftentimes students do not evaluate these functions at the port planes. So they'll figure out what the incident wave is as a function of z, and they'll figure out what the scattering waves are as a function of z. But then when they find the scattering parameters, they just leave the functions of z in there. And so all of a sudden the scattering parameters become a function of position along the transmission line. Well, that has no physical meaning at all. The scattering parameters are numbers, complex numbers. And so what we do is we take our scattered voltage, for example, on the first port, and we evaluate it at the port plane. Whatever the index is that defines the location of the port plane, we put that number into our function, in this case the scatter wave function, z1, make it set it equal to 0, and then this is the result. Notice this result has no index z anywhere. It is a complex number. Same thing for the scattered wave at port 2. We evaluated at the port plane for port 2. In this case, we called it z is equal to 0, is the location of the port plane. That is typically the case, and again, it makes the math nice. This goes to 1, but sometimes it's not. So make sure that you interpret or evaluate this correctly. This would be the result for the scattered wave at port 2. And then finally, what is the value of the incident wave at port 1? We evaluate it at the port plane, and we get a complex number, not a function of position, a complex number. This is the value of the incident wave at port 1. 3 complex numbers. Now we can go through and determine the scattering parameters. So we know that the scattering parameter S11 is the ratio of the normalized wave amplitude B, this is the scattered wave, the exiting wave, at port 1, divided by the normalized wave amplitude A at port 1. This is the incident wave. Since it's A, it corresponds to the plus wave, or in this case, the incident wave on the port. So we go through, here is the definition, by definition, the normalized wave amplitude B1, and this is the inverse of the normalized wave amplitude A1. We know what the value of E1 minus is at our port plane. We just calculated it on the previous page. Likewise for the incident value. And so we insert those results in there and do a little algebra, and this becomes the result. This is S11 for that device. Notice it depends on ZL. Seems like it probably should, since that's really the only parameter in the two-port device itself, but it also depends on Z0, the characteristic impedance of the transmission line connected to it. Remember, the scattering parameters depend on the characteristic impedance of those transmission lines, and clearly it does in this case. S21, the same thing, except for we use B2, the normalized wave amplitude, the scattered wave at port 2. We calculate what it was on the previous page, and we insert it and do a little algebra, and this becomes the result. Notice S11 is different than S21, but they both include both ZL and Z0. All right, so there are two very important things to note about these results. So the first very important thing to keep in mind is what I alluded to in the previous slide, that the results depend on the load impedance ZL and the characteristic impedance Z0 of the transmission lines. And this is in contrast to what we would have for the same device if I determine, let's say, the transadmittance parameter for that device. The Y11 would be 1 over ZL, and Y21 would be minus 1 over ZL. Again, these are the transadmittance parameters for that two-port device. Notice here the results depend on ZL, that series impedance, as they must, but they don't depend on the characteristic impedance Z0. And of course, that's one of the big differences between impedance parameters and admittance parameters and scattering parameters, is that the scattering parameters depend on the device and the characteristic impedance of the transmission lines connected to it. Again, what we're trying to do is analyze this two-port device, how it works when immersed in a matched system, when connected to transmission lines with a characteristic impedance of Z0. And so our scattering parameters need to reflect the fact that they are immersed in this matched system with values of Z0. Again, no such analysis occurs. We don't care what the transmission lines are if we're talking about impedance or admittance matrix. So this is just reiterating what I just previously said on the previous slide. Again, admittance and impedance parameters, the admittance and impedance matrix do not only depend on the device itself and not on the characteristic impedance of the transmission lines connected to them, whereas for scattering matrix, they depend both on the device and on the characteristic impedance. Again, we're seeing how this thing works immersed in a matched system. So to put it another way, this, if you look at the scattering parameters, what are we doing? We're evaluating the relationship between the scattered waves and the incident waves. And of course, those scattered and incident waves are propagating on a transmission line. And so we need to say somewhere in the analysis what the characteristic impedance of that transmission line is. And so that's why the scattering parameters, another way of looking at why the scattering parameters depend on the characteristic impedance of the transmission line, because in the end, we are analyzing the waves propagating along those waves, both incident and reflected. To emphasize this point with a numerical example, let's say our series impedance here has a value of 100 ohms. All right, 100 ohms real, 100 plus J0. So we get a 100 ohm resistor in series. And let's say that the characteristic impedance of the transmission lines connected to either end is 50 ohms. We use our result we got for S11 and S21, and we find it just so happens in this case that they both have the same value of 0.5. Again, this is not usually the case. Clearly, algebraically, they aren't equal to each other, but for the values that I selected, it turns out they both have the value 0.5. So now let's do something different. We're going to keep the device the same. The two-port device is precisely the same device as it was before. It is a series impedance with a value of 100 ohms real. The only difference between this case and the previous case in the previous slide is that we're going to change the characteristic impedance of the transmission lines connected to it. Before we had 50, now we're going to make them 75 ohms. So now we're going to recalculate S11 and S21, and what we find is we get a different answer. 0.4 for S11, point 6 for S21. Notice we haven't changed our device at all. The only thing we changed was the characteristic impedance of the transmission lines connected to it. Same device, but different scattering parameters. And hopefully this shows that the scattering parameters depend on the device itself, but also on those characteristic impedances. Change the transmission lines, you get different answers. I said there were two important things to remember about scattering parameters. This is the second. Scattering parameters depend only on the physical parameters of the two-port network and the characteristic impedance of the transmission lines connected to it. Now, this sounds very similar to thing number one. The only difference here is the word only. Before I said scattering parameters depend on the device itself and depend on the characteristic impedance of the transmission lines connected to it. And that's, again, important that we understand both of those things are going to affect scattering parameters. This point says only those things will affect our scattering parameters. Only is a very important word in this message. So important thing number one said that scattering parameters depend on the physical parameters of the device and the characteristic impedance of the transmission lines attached to that. Important thing number two added this third clause, which is that it depends on nothing else, absolutely nothing else. These two things and these two things only. So I emphasize this because students often provide me with answers that violate that third clause. They have scattering parameters that depend on Z0 and the device parameters, but also there are other things thrown in the solution. So I see something like this, where there's a voltage involved in S1, or like this, where there's some current involved with S21, for example. And these results can't possibly be correct. We can't go through the scattering parameters of a device don't change if we change some voltage or we change some current. Scattering parameters define the physical reality of the device. They are what they are, whether that device is in one circuit or another circuit, whether it's sitting in your desk drawer. The scattering parameters don't change dependent on some external stimulus like a current or voltage. So they have to depend on things like Z0 and some impedance, some length of transmission line, whatever the physical parameters of the device are, but they cannot depend on voltage and current. And I will add to that, they cannot depend on the index Z on our transmission line. Again, I get that a lot because people don't evaluate their waves at the port plane, and so I get answers that depend on the index Z1 or index Z2. And again, that can't possibly be right. It really has no physical meaning at all, and I'm not particularly a generous or patient when I see that on an answer, because that doesn't even pass the sanity check or the plausibility test. It's an answer that has no meaning. Now, I've had through the years a handful of cases where students were not happy when I took off many points for having a scattering parameter with a current in it or voltage in it, and they argue that this is completely plausible and reasonable. After all, look at Ohm's law. The resistance is the ratio of V over I. R is a physical parameter, and it depends on the voltage across the device and the current through the device. But of course, that's a horrible interpretation of Ohm's law. It's not what Ohm's law says at all. We can't go through and alter the resistance of a resistor by placing a different voltage across it or a different current through it. Ohm's law is not a statement for how do we manipulate the resistance of a resistor by selecting different voltages and currents. No, Ohm's law is a constraint equation. We have a resistor of a certain resistance, 1 k ohm, and that resistor says you can put any voltage across me you want, but the current is going to be then that voltage divided by 1,000 ohms. Or you can put any current through me you want, but the voltage that results is going to be that current times 1,000 ohms. It is a constraint that couples the voltage and current based on the resistance. We don't alter or change the resistance by changing the voltage or current across a resistor. And it's the same that goes true with scattering parameters. We can't change the scattering parameters of a physical device by turning some voltage up or turning some turn current down. Again, those are nonsensical statements. If we look at resistor, for example, what we find is it depends on the physical parameters of the device, just like the scattering matrix does or the impedance matrix does. Resistance, if I want to alter that, I need to, in the case of a uniform conductivity cylinder, I need to either lengthen the cylinder, or I need to reduce the cross-sectional area, or I need to reduce the conductivity if I want to change the resistance of the device. The same thing for capacitance. Again, it doesn't depend on the voltage and current, voltage across it or current through it. It depends on the physical parameters, and that's what we're after with the scattering parameter, is equations that look like this. They have no voltage or current in them, and they certainly don't have any functions of time or functions of position.